This is the Math 2 lesson summary video for the lesson entitled iNumbers. The purpose of this lesson is to discover which sets of integers, rational numbers, irrational numbers, real numbers, or complex numbers are closed under the operations of addition, subtraction, and multiplication. We will be using the operations of addition, subtraction, and multiplication among these different sorts of numbers in order to figure out if statements are sometimes, always, or never true. In Lesson 9, iNumbers, we are extending our number system to include complex numbers because of our previous lessons and what we've noticed about our quadratic functions. We have now discussed that when the quadratic function does not cross the x-axis, the parabola is said to have imaginary solutions, and we have learned how to write those in complex number form. In this lesson, first we are given a diagram regarding our numbers in mathematics. So we can see that the outside of this rectangle, there are complex numbers, and inside there's an inner rectangle that includes real numbers. Real numbers are all the numbers you have thought up to this point in your high school career. So we have natural numbers, whole numbers, integers, rationals, and irrationals. All of those are real numbers. And outside those are what we call our complex numbers. So what we're going to do is we are going to work through a few of these conjectures. Remember, conjecture is an educated guess. We're going to provide 3 examples to show if our conjecture is true. And if we do find one that is not true, we're going to call it a counterexample, and that will prove that it's sometimes not true. So for conjecture 1, we are asked to find that the sum of 2 integers, if it's always, sometimes, or never an integer. So if we look at 2 numbers, I could take, for example, 2 plus 3. Those 2 numbers are integers, and we're trying to find the sum. So in this example, we would see that our answer is 5, which is definitely an integer. We can give another example, like 7 plus 2. Those are both integers, and when we add them, we get 9. That is also an integer. And a third example we could give is 5 plus 6, which gives us 11. That is also an integer. So we can see that the sum of 2 integers is always an integer. Moving along to number 2, we are asked if the sum of 2 rational numbers is always, sometimes, or never a rational number. So we want to find 3 examples. If we take 3.1 repeating plus 3, we know that we'll get 6.1 repeating. And recall that that is indeed a rational number. If we take as a fraction negative 2/3 plus 3/5, that equals negative 1/15, which also is a rational number. And negative 3/4 plus 3/4 equals 0. And 0 is a rational number. So that is always true. On conjecture 3, we are asked if the sum of 2 irrational numbers is always, sometimes, or never irrational. So if we look at some examples, we can take the square root of 2 plus pi, and we can see that the square root of 2 plus pi is equal to 4.5580, so on and so forth, which is an irrational number. So that definitely checks. If we look at the square root of 2 plus the square root of 8, which are both irrational numbers, we can simplify the square root of 8 into the square root of 4 times the square root of 2. The square root of 4 is 2, so therefore this is equivalent to 2 root 2, which is still irrational. If we try a third example, root 2 plus negative root 2, we get 0. Now when we get 0, that proves that it's not irrational always, in that the sum of 2 irrational numbers will sometimes be an irrational number. On the fourth conjecture, we're asked if the sum of 2 real numbers is always, sometimes, never a real number. So if we take root 2 plus root 2, which is a real number, each of them, we get 2.828, so on and so forth, which is irrational. And irrational numbers are real numbers, so that works. Moving to another example, if we take two real numbers, 2 plus root 3 plus 3 minus root 3, we'll get 5, and 5 is a real number. If we take 2/3 plus 4/5, which is 22/15, that is a rational number. So that is also a real number. So we would say that this is always true. On conjecture 5, we are asked that the sum of two complex numbers is always, sometimes, or never a complex number. So recall that a complex number is in the form a plus or minus bi. So we're going to choose some complex numbers to add together. So if we choose the complex numbers 3 plus 2i plus 4 minus 3i, we can only add the real and the imaginary parts together. So when we add 3 plus 4, we will get 7. And when we add 2i minus 3i, we'll get minus I. That is definitely a complex number. If we try adding 3 plus 2i plus 4 minus 2i, when we add the real parts together, we'll get 7. And when we subtract the imaginary parts, 2i minus 2i, we'll get 0i, which still is a complex number. And the last example that we'll look at is 5 plus 2i plus negative 5 plus 2i. When we add our real parts together, we are going to get 0. When we add our imaginary parts together, we will get 4i, which is still a complex number. So we can see that this is always true. The sum of two complex numbers is always a complex number. When we look at conjecture 6, the product of two integers, we discovered that it's always an integer. So I'll give one example here. You can come up with two more, but these are both integers, and we see that the product is always an integer. When we look at conjecture 7, the quotient, which is division of two integers, is, and we determine that is sometimes true because we came up with a counter example. For example, the example we came up with in class was 8 divided by 3. And 8 divided by 3 is equal to 2 2/3, which actually is a rational number. So therefore, this is what we call a counter example. It's an example that proves that our conjecture is false. So this only sometimes works because if we look at an example where it does work, such as 8 divided by 2, we see that it's 4, and that indeed is an integer. So that definitely works. Looking at 8, the conjecture was that the product of two rational numbers is always, sometimes, or never a rational number. We determined that that is always true. We looked at some examples such as, and product means multiply, so we took some fractions and we multiplied them together. And when you multiply fractions, recall that you multiply numerator by numerator and denominator by denominator. There's a rational number. And if we look at another fraction, 3/4 times 2/3, we get 6/12, which is 1/2, which is also rational. And if we keep looking at fractions and multiplying them, we will see that this always works. The quotient, when we divide two rational numbers, we will always get a rational number. In conjecture 10, we are asked to find if the product of two irrational numbers is always, sometimes, or never an irrational number. So this is actually sometimes true because we can provide a counterexample. And the counterexample we can provide is if we take the square root of 2, which is irrational, and multiply it by 2 root 2. We are going to get 2 root 4. And we know that the square root of 4 is 2. And 2 times 2 is 4. Therefore, 4 is not an irrational number. So this here is a counterexample that proves that this is not always true. But we can provide other examples that prove that it does work in other cases, such as if I take the square root of 3 times 2 root 2, I will get 2 root 6, and that is indeed irrational. In conjecture 11, we are now asked if the product of two real numbers is always a real number. And we did several examples. We know that that's always true. And finally, conjecture 12, if the product of two complex numbers is always, sometimes, or never a complex number. Well, let's go through the multiplication here. So let's multiply two complex numbers, 3 plus 2i times 4 plus I. And in order to multiply, we do need to distribute the 3 and the two terms in the second. So we're going to do that. 4 times 3 is 12. 3 times I will be plus 3i. 2i times 4 will be 8i. And 2i times I will be 2i squared. If I combine my like terms, I will get 12 plus 11i plus 2. Recall that I squared is equivalent to negative 1. So we can replace that with negative 1, and we will get 12 plus 11i minus 2. 12 minus 2 is 10. So we can simplify this into 10 plus 11i, which is a complex number. If we do more examples where we multiply, we will see that this is always true. The last one we're going to look at is the ratio of the circumference of a circle to its diameter. Now recall the circumference of a circle is equivalent to pi times diameter. So it's saying that the ratio of the circumference of a circle to its diameter is given by an irrational number pi, which we see right here. Can the diameter of a circle and their circumference both be rational numbers? Well, let's plug in a rational number in for the diameter. So in the calculator here to the right, I plugged in 2/3 as my diameter, and my output was 2.09. It was an irrational number. So that tells us that when we plug in a rational number for the diameter, we will not get a rational answer for the circumference. So this is no. We can't multiply an irrational number by a rational number and still get a rational number. If you need more help on the Ready, Set, Go homework for this task, please check the Canvas Student Support site.